Hi everyone, in this video I'll show you the final project of an embedded Linux course. I've designed digital Theramin using Raspberry Pi, a TOF 1020 distance sensor and a Yamaha digital piano. The system converts hand movements into MIDI notes in real time, just like a real Theramin. Let's dive in! The core of this project is a Raspberry Pi running embedded Linux. It's connected to a TOF 1020 time of flight distance sensor over the I2C bus. For this project, I wrote a custom driver that reads distance values from the sensor. The data is processed by a user space application that translates the distances into MIDI notes. As I move my hand closer or further, the sensor measures the distance and sends it to the Raspberry Pi. The Raspberry Pi is also connected to this Yamaha digital piano via USB, which plays the generated MIDI notes. This is the layout of the project. I'll walk you through all the software components that made up this Theramin Raspberry Pi project. There are two folders here in the main repo. One for the TOF 1020 driver, kernel driver, and one for the Theramin application, user space application. The Theramin, the TOF 1020 distance sensor is TOF 1020, and from the source code here you can see the functions that access I2C to get the value from the sensor. So this is the main function to get the distance. It uses the Linux I2C driver. First it gets the adapter using I2C bus number 1. The device address of this TOF 1020 is 52 hex. And the register that I'm reading for the distance is address 0. So that's the function to get the distance. After getting the I2C adapter, the message is filled with the I2C address, device address, and this is a write operation. We write the register address, and then the len is 1, because this is 1 byte register. And the second message here is the read 2 bytes, and that's the data pointer to get the data, to get the 2 bytes out of the distance, out of the TOF 1020 sensor. Then if the transaction fails, I'm printing to the kernel message that the I2C read has failed. The distance returned is -1. This indicates to the user that the read is invalid. If the read was valid, then the distance is comprised of those 2 bytes. The first one is the MS byte, and the second one is the least significant byte. So this is like a big Indian system, where the MS byte is written first. And finally, release the adapter that we acquired here with the get adapter function. The function TOF 1020 read is calling this utility function get distance and fills the data to the user. This is basically similar to the AESD char device that we did in the course. And number of bytes returned is 2. So I implemented only the read function here, as well as the open and release, of course. Okay, this is the init module, nothing special about it, and clean module. This is the terminal of the Raspberry Pi. To make it easy, I made an alias for a hex dump of 16 bits. So I'm using the hex dump command to display a 16-bit word. And if I'm calling hex dump 16 on /dev/tof1020, I'm getting the distance. Now the distance is 7d0 because my hand is not blocking the sensor. And if I'll put my hand above the sensor, I can get different readings. I'm moving my hand now and I'm getting different readings on each read. This is basically the implementation of the TOF1020 driver. The Theramin user space application uses the driver. First, I open the device. So this is the /dev/TOF1020. And using this file descriptor to read 2 bytes every time in a while loop. And if the value is -1, I know it is an error. Sometimes the I2C gets error. I am ignoring this error and continuing, putting the value to be 1 just so the while loop will not exit. And then there's a function here that calculates the absolute value of the previous value that I read minus the new value, and if it is bigger than 50, I'm handling this reading. The reason I did that is to clear the noise when the sensor reads gives a reading. The read keeps changing, right? So I would like to make sure that only if the read changes a lot, then it indicates that this is a new read, a new value to handle and to send a note to the MIDI. In this while loop, I'm sleeping here for 50 milliseconds to make the sample rate here of 20 Hertz. So I'm sampling 20 times per second the value of the distance sensor. In addition, this user space application utilizes the ALSA module library from Linux to access the MIDI controller. The Yamaha digital piano is connected via USB into the Raspberry Pi, and the ALSA kernel driver detect that, and we can see this device if we run ALSA MIDI -L. No card found because my USB is not connected. Let me just connect the USB from the Yamaha, and now when I read, I can see that there is a device. This is the Clavinova MIDI 1. This is the hardware identifier for this MIDI device, and I'm using it to open the MIDI port in the code. So using this port name, I'm using the ALSA API to send the command raw MIDI open, opening this MIDI device, getting like a handle to it. This is the raw MIDI data structure that I use whenever I want to send MIDI commands to the piano. The play value is a function that gets this MIDI device that we acquired, as well as the value that I read from the sensor and a maximum val. I have limited the distance that I read from the sensor to this value, 180 hexa, because I wanted to limit the range and map it into 1 octave on the piano, just to make things sound nicer. This also uses for the normalize function to scale down this range into the range of those notes. So this is an array of all the 8 notes of the octave from C3 to C4, and I skipped all the half tones here, again for the purpose of making it sound nice. And that's a helper function for sending a MIDI command for note on and then note off, and this is for playing a note. So play a note is sending note on, sleep for 100 milliseconds, and then send a note off command. And the function play val is using this play note after mapping the value into a note. So the note index starts from 0, and then added into it the total notes times the value divided by the max value. So this is the scaling or the mapping between the value I read from the distance and the note index. And then the note index is used to access one of the notes in this. As we saw, this is a 1 octave starting from C4 to from C3. Just kidding, that's not a real demo. Disconnected the MIDI from the tablet and connected it now to the Raspberry Pi. Now let's start the application. That's it. That's the demo. One of the biggest challenges was writing the kernel driver and tuning the MIDI note mapping to make it feel responsive and musical. I learned a lot about real-time processing and embedded systems. That's my Raspberry Pi Theramin. I hope you enjoyed this project. If you have any questions or ideas, feel free to leave them below. Thanks for watching.